Okay. For our last session, we have Joe Gordon, who's going to speak about large-scale identification of race conditions in OpenStack CI. Joe is a Nova core, probably wears other hats that I'm unaware of. Yeah?
I'm unaware of them too. So.
Yeah, okay. And yeah, well, please welcome Joe.
Hi, so thank you to Anita. Jeez, this is loud. Sorry. Thanks to Anita for introducing the log stuff a bit. This sort of ties into that. A big part of this actually is trying to understand the logs and use them for useful things. So OpenStack, you guys have probably seen this image by now, so I'm just going to sort of skip it. OpenStack is a big thing, provides lots of stuff, yada, yada, yada. Hopefully by now we all know what this is, right? Yes? Great. OK, so OpenStack is really, really big in development scale. We're just simply massive. I think we're the biggest Python project that's open source that I know of. If anybody here thinks that's incorrect, please let me know, because I haven't found any better numbers than this. Past 30 days, we've had almost 500 contributors, and past 12 months, we've had 1,861,000 commits. So we're really big. We're a lot of commits, a lot of code. Over 2 million lines of code. This is by Olo, so this is a bit of a third party that's hopefully less biased than some of the OpenStack folks themselves. So with the scale, there's a lot of complexity. We have some development principles when we're working on OpenStack that we sort of try to follow that dictate a lot of our processes. And they're never break trunk, so that's why I have all this testing. We generate tons and tons of tests every day. You saw that we generated over 1 million test slaves the past few months or whatever that was. So never break trunk. We don't want to block each other. If you're a developer, you're working on a piece of code, you download it from Git, you download a trunk, and it's broken. You get really upset. Nothing's working. Now you can't do your work. And that causes a lot of problems. This also helps support the continuous deployment process. So unlike most projects, we're supporting stable releases and continuous deployment. So you should be able to deploy from trunk on any given day of the week, anytime. This is actually being done by Rackspace and HP public clouds. Both of them are, I think, within about 6 weeks of trunk. So the code we write today gets pushed out to public clouds in a matter of weeks. And this actually leads to all kinds of complexity. We can't just do a stabilization period late in the cycle. If we know things are broken in trunk, people are going to be using it broken. So we can't let that happen. Transparency. We try to do everything in the public. We're a big project, and if we do everything secretly, it makes it really hard to scale. Automate everything, the same reason. At this scale, we can't run things manually. We don't want to run tests manually. It's just not really a... Yeah. Sorry. Running things manually is not really scalable, and people forget about it. You forget to run pep8 even, and imagine if we had to run all the tests manually. Egalitarian, this is for the same reason. It's a big project and do everything out of the open. Everybody has a voice in everything if they choose. And the last one's a bit more controversial, but be strict and want to reduce the burden on reviewers. So a big part of this is a reviewer. The most constrained resource right now at OpenStack is the human reviewer. So we have a lot of developers, we have a lot of reviewers, but we don't have enough reviewers. So we try to remove the burden off the reviewer. So a reviewer doesn't have to check for style correctness. We have a pep8 job for that. We don't have to check for the unit test passing or integration test passing. So we try to do as much as possible to move the burden off the human reviewer and push that into an automated system that is a bit more scalable than the humans are. So what happens when you submit code? Who here has actually submitted a patch to OpenStack? OK, a good amount. I don't think Josh has. So a lot of things happen automatically. So we do a whole bunch of things right away. So we have a pep8 job. You write your patch, push it into Git, type in git review. It goes up to our Gerrit server. And then behind the scenes, a whole bunch of things happen thanks to our great infra team. The pep8 jobs, that's for style correctness, to make sure that's correct. We don't want the humans to really care about that too much, although as a team, we like the code to look the same. And so it's important for us to enforce some sort of style formatting. Unit tests, we want to make sure unit tests are always passing. We generally test against Python 2.6, 2.7, and we're starting to migrate to 3.3 and off 3.3 and now on to 3.4. So 2.6, I think, is we're going to drop 2.6 in the next release. 2.7 is going to be the big one, and we're trying to move to 3.4 compatibility as soon as possible, which may take a long time because we have a lot of dependency issues. DevStack Tempest, this is our big integration environment. And DevStack Grenade, this is our upgrade environment. This spins up an old DevStack and then upgrades everything and puts it into a new DevStack. So this goes, for example, Icehouse to Juno is what we're doing right now. And this is because we believe upgrades are important, and we want to make sure they work at any given time. So in a single dev stack environment, and we have several of these on any given test, we'll run Postgres, MySQL, we'll run against Neutron, Nova Networking, and a whole bunch of other parameters. We run about 180 VMs inside of every single dev stack environment. So this is a really big system, and we're generating tons of data out of every single job. So this is an example of a real patch. This is what happens when you submit a piece of code to OpenStack. So here's a little, a tiny doc change. This is not even a code change. It goes up, the tests get run, and they fail. This doesn't work, right? Something's broken here. What happened? Why does making a doc string change break all the integration environments? That's not supposed to happen. So there's a lot of data in here, and it's hard to sort of interpret all this data. And what happened in this whole system is you generated 5 to 10 dev stacks in any single patch, over 10,000 integrated tests, thousands of second-level guests inside of our dev stack VMs, and about a gigabyte of data per job. So we're generating tons of data in the jobs, and that's what Anita was talking about, is reading that data is really hard, actually. And this adds up to a lot of stuff every week. On an average given week, we've got 250 to 500 changes are merged. That's not considering patches up for review. That's actually code landing into trunk. 15,000 to 30,000 change revisions per week. And just to give a nice point in time, a reference, it was about 10,000 new first-time changes proposed in every 42 days.
What's the first-time change? Is that the first time someone pushes a change?
Yes. So the Garrett ID number, we went from 70K to 80K in 42 days, and 80K to 90K in 42 days, roughly.
You mean
every new patch, not a revision of a patch.
Okay, so I thought you were talking contributors, which means that first-time change.
Sorry, that's not clear. Yeah. It's for a new patch, so not a revision of a patch, a new patch. So we're generating tons and tons of jobs any given day of the week and every day, et cetera. So we have large numbers here, so some basic probability of large numbers. We have a few basic factors here: the chance of the event, the number of events per run, and the number of runs. So here's a real example, actually. Some of these numbers are a bit made up, but this is a basic. They're very close. So let's just say GitHub is down 0.05% of the time. That's actually pretty good uptime, and this is probably close to true. With that failure rate, we have about 20 clones per run, and we have 1,500 jobs per week. So that means GitHub is failing in 15 jobs a week. So that means 15 people write a patch that changes a doc string, and it fails because GitHub is down. As a conclusion, we actually no longer use GitHub for cloning things. We have our own Git server because of this. GitHub rate limits you. They're not designed to be, supporting a CI system. They're of a different purpose. So we've seen this in numerous times, that even if something fails 0.05% of the time, that is way too much. So this comes from another picture you guys have probably all seen too many times today, which is this is actually a really old picture at this point, but OpenStack has a lot of services. We actually hit a point. We had a bug in our integration environment where Postgres was falling over because we had too many connections with the default config. I think that was about 100, 150 connections. So in a standard job, we actually have about 100, 150 processes talking to Postgres. So this is a really big system, and this is all on a tiny machine. There's a lot of moving parts here. So how we used to do this. Back in Grizzly, something would fail. We had a tool, because that happened, we had a tool to run Recheck. So you just type in Recheck, and you look up a bug number. You try to figure out what it is on your own. And then hopefully you would pass the second time. And nobody actually really knew what the bugs were, and this was a big mess. This is actually a real example of something that happened. Somebody had a big patch series. We like to break our patches up into small, reviewable chunks. Somebody had a big patch set that was 15 deep. So they put it up. The patch set fails. A third of the patches fail. They run Recheck, and a different third of the patches fail. And then the guy goes, hey, have you seen this failure? And they point to a URL, and it's a giant stack trace in a random file. And it turns out the brain is not a great big data solution. You look at it, you go, I don't know. Maybe I saw this a week ago, maybe not. Then we turned on parallel testing. At the time, we were running one run test worker on an entire integration environment. And then we did it in parallel, and that broke everything. And that's thanks to Matt over there. He didn't break things, he just facilitated the breaking. And that really put us really far back. It turns out we were testing a really simple test scenario where one person was talking to your cloud. That's not really what happens in reality. I think we're about at 4 workers now, and when we first switched over, we broke everything all the time. So we really needed a better solution than just looking at 1 gigabyte of logs and trying to figure out what happened, and then somebody else hits it, and they have to figure it all over again. And then we're wasting a lot of reviewer time, a lot of developer time, and there's a lot of people are freaking out. They don't know why their patch is failing. They have to sit down and spend half an hour, a day, a week, figure out why the patch failed. Or they just don't care, and they let everything fail, and we have too many failures in the system. So this is the key question we're trying to answer. So have you seen this recently? The old tool was Recheck, and we started to use we have a new tool now called Elastic Recheck. So instead of a stack trace, have you seen this recently? We're using Kibana on the front end to actually look at things. So now we can actually you can type in a query, so a stack trace, for example, something in the console log, something in an OpenStack log. You could type it in here, and we can actually see it plotted over time. So we can see if it's coming up. We could dig into it more. We have some metadata associated with it, what jobs it's running on. Is it a Postgres job only? Is it a everything job? Is it a unit test job? Things like that. Have you seen this recently? So we take this data and we're actually pushing it back to the reviewer. So now what happens, you push a patch up to OpenStack. Instead of getting these failures, we actually go and tell you, hey, we think you failed for these reasons. So now you can actually go through and validate that, yes, you hit some known bugs. And you could type in recheck whatever the bug was, and you don't have to waste half a day trying to debug what happened with your patch, and it wasn't your fault. And we've seen this recently. So we want to actually track the bugs going through the system. So we actually have a page to track the most recent bugs and the trends of them. So we sort this page, by 24-hour increments. So the top bug in the past 24 hours. And now if you're interested in seeing what's failing in the system and the biggest bug, you can just go to a single page and you list all the bugs out, and they're sorted by the big ones of the day. So going back to what happens when you submit your code with this Elastic Recheck system. So this is a bit of a crazy-looking graph because it's a bit of a big, crazy system. And we have a lot of big moving parts in here, and it's a big asynchronous system as well. So the tests complete, they go through your job runner. We take all the artifacts, we store them in logs.openstack.org, as Anita mentioned. But we also take a bunch of the logs, and we put them in logstash.openstack.org, which is a big Elasticsearch cluster. I believe it's, you know how many machines it is? 20 for the, yeah. 20 for Logstash workers, and I think it's 16 for Elastic. So there you go. So Logstash workers are taking the data, they're processing them, adding metadata, things like that. They're formatting them. And then they put them into the actual Elasticsearch search engine. So as you can see from those numbers, it's a huge system. We're only able to store about 10 days of logs right now, and we commonly get backed up. We don't have enough Logstash workers. So even with this big system, it's actually quite slow. What? Yes, everything is VMs. I don't think Infra has any real machines that I know of. Infra has no hardware. Yeah, so this is all on virtual machines. That's correct. So we take all these logs, and we don't actually store debug logs in here because that would be too much data. We wouldn't be able to store anything in there. So I said this is only 10 days of data. We went down from 14 days because we didn't have enough space. From there, we actually do 2 things with the data. One is we build the static web pages, and we have a job that runs every 30 minutes or so and updates the Elastic Recheck page with the unknown bugs, as I'll get to, and the list of the most frequent bugs. And we also take that data and we hook into the Gerrit stream of the results of your test completed. And we actually have a bot that'll go through and run Elasticsearch queries against Elasticsearch with known fingerprints of the bugs. And if it finds a bug in one of your jobs, it'll report back on IRC if it's an unknown bug. So if you found a bug in the gate job, which the gate job should never fail because it already has been checked many times, and we are assuming it's clean, we'll report that into an IRC channel for tracking. And we also, we'll report the data back into the Gerrit system. So if you put your patch up and it fails because of GitHub went down, we don't have that anymore, thankfully, but that used to happen. It'll report back saying, hey, you failed because of this bug. We know about it. You could run this command, and it'll retry. We don't actually automate the retry loop because we're human and we're afraid we'll make a big mistake and have an infinite loop. Furthermore, the system fails open, so we only look for if this failure, if this known issue hit your job, but that doesn't mean no other failures hit your job. So this is to help people, but this isn't, you can't assume nothing else failed in it. And furthermore, you have to be careful about the bug, and you should always double check. The fingerprints are never perfect. We have false positives all the time, and we try to fix those. So when we started this, this is actually started by me and a few other people, Matt Tranish and Sean Daig. We thought there was going to be about 6 or 10 bugs in the system. We were having a lot of problems in the system. We weren't able to land code. Everybody's running Recheck. Nothing was happening. We just figured there must be about 6 or 10 big bugs in the system. We'll fix those 6 or 10 bugs, and that'll be it. Everything will work. It'll be great. It turns out we were completely wrong. There was, I think right now we're tracking about 130 bugs today. I think it was 136 when I checked this morning. It's not 6 or 10 bugs. 6 or 10 bugs is what a human could sort of remember. And that goes back to the have you seen this bug. I can't remember 130 bugs, but the system can. I can remember at 6 or 10 bugs at best. So that's why we sort of saw that. It turns out we have all kinds of crazy bugs. We have a lot of the bugs are well under 1% failure rates. We have bugs that will hit once a week, and those are consistent. We have all kinds of bugs in the system. We have some upstream service problems. PyPy would go down occasionally. GitHub, DNS issues. We'll have upstream vendor problems. Upstream app mirrors we use. App mirrors are not always perfect. Sometimes they'll break and they'll get in a strange state when they're getting updated on the back end, and that'll break all kinds of things for us. As a result of this, we cache a lot of things, and we assume touching the network to pull things down is dangerous, and we try to mirror everything we can ourselves. We have our own PyPy mirror. I don't think we have our own app mirror yet, but that's in the works. We don't pull things from GitHub. We cache things from our Git servers when possible, and all kinds of things like that.
There's still a few things that use GitHub. Are they cached locally?
I think we pull down installing pip from GitHub, and it makes me cringe every time I see it. I think that's the only one. And I don't think it's...
No VNC as well, which is still GitHub.
Oh, anyway, so those are still there. I don't think they're cached. I'm not sure, though. That's a good question. We have some infra problems. We'll get bad node pool images. We've had this. I think we actually have this all the time. This is actually a pretty bad one. It'd be nice if we had a better way of getting around that. Service outages, we'll get that all the time. Something happens with the upstream provider, something unavoidable. And mirrors break. It happens. We also have a lot of bugs in OpenStack. It's a big system. It's written in Python. It's written by a lot of people. And it's a big asynchronous system, so it's going to have a lot of issues in it. State corruption races with asynchronous messaging. It's a really, really big asynchronous system with lots and lots of asynchronous workers. So we get a lot of these problems. Database deadlocks, we got a new big one today, or the other day, I think, actually. We always have a few of these in the system. Once again, a lot of workers. It's a big system. This happens a lot, unfortunately. Races with multiple workers, all kinds of things. We had issues with, we had a Keystone middleware problem where it wasn't updating files atomically. We get, you name it, we've seen it before. And these things sometimes hit often. Sometimes they'll hit 30% of the jobs. Sometimes they'll hit 1% of the jobs. So 1% of the jobs is still massive. We have bugs in tests. We'll have unsafe global state. So once we hit multiple workers, all of a sudden these unsafe state problems were really apparent to us. What? Yes, and there's still a single node. That's a great point. We're actually running everything in one node. So OpenStack is designed to run on many, many machines, but for restricted resource problems, we're running this in integration environment on one node for now, and we have all these bugs.
That's actually changing.
Right, that's changing soon, and we'll see how that goes. That should be interesting, bug-wise. Comparing timestamps when you fix things to run in parallel, things, every so often somebody puts a bad test in that checks a timestamp and it runs too fast or too slow and it breaks. And we fixed a lot of these bugs, and I don't think we're seeing too many of these now. We've seen bugs and dependencies. We've seen libvirt bugs, I think, constantly, unfortunately. We actually are really aggressive on libvirt. We're hitting it. All our tests run on libvirt right now on the gate. So we're running thousands of these libvirt jobs a day. On each job, it's about an hour long. We're spinning up, over 100 QMU machines inside of it. So we're actually really abusive of libvirt today. And that's one of the reasons why we see so many problems in it. We've seen some really bizarre bugs. We've seen a bug with the kernel network block device. If you're doing file injection and you had a neutron set up on the same machine, it would break things. And why this happens, I'm actually really not, it's not clear to me still. But you wouldn't think, oh, file injection would break, neutron. It's not supposed to work that way. But we've seen things like that. We've seen a problem in, we had a file descriptor leak in HTTP-lib2 that it was causing crosstalk between RPC and REST APIs. So we're getting REST calls on RPC buses and vice versa. And that took, I think, about a month of 3 or 4 people solid to fix it. We see the craziest bugs. It's really bizarre. And we usually get through them, but sometimes they take months and months and months. And that's where it's really nice to be able to track these bugs and see how, be able to triage them really well. We've actually had to get libvirt versions backported from Canonical for us and all kinds of things. In fact, Canonical has a pretty sane policy of asking for tests to detect the bug for aggressions. And we told them we don't have one. And it took a while for us to convince them that. But we could barely, reproducing it means running 1,000 jobs. And we do that every day, so that's easy for us. But for Canonical, that's a little harder. So contributing patterns. So a pattern for a bug, what happens, your patch fails, you find the bug, let's say, and you want to write a query for it. So you go through the logs, you find a query, you find a stack trace. That's usually a good telltale sign of a bug. We use Elasticsearch for this, so it's the Lucene query language, and everything's in Git. So you can actually go to git.openstack.org and go to OpenStack info Elastic Recheck and put a patch into the queries. And the format here is just the bug number and then .yaml, and then it's a query, and then it's the actual query itself. And you put that up, and you write a little commit message, and you push it in. And now we can actually track this bug and report back on individuals' commits on individual patches if they see that bug, and we can actually track in the priority of and the trend of it. We have another thing we could do with this data. Now that we actually are able to classify failures, instead of just going through and classifying failures as a failure comes in, we'll actually go through over the previous failures in the system, and we'll actually we have a list here of unclassified failed jobs. So this is really nice for us if you want to help us out here. This is a great place to start. You look at a job. We have the list of the jobs on the right, and we break this down to either click at 1 day, 2 day, 7 day, or 10 day list. And this is the list of all the jobs that have failed for unknown reasons. So we try to keep the classification rate, categorization rate about 80, 90%. Anything lower than that means we have a really serious bug. In fact, we caught a bug today, and that was one of the reasons why I think our classification rate today is about 80%, maybe a little lower. And that's because we had a big bug in there that we just caught. Some next steps. One of the big things we're trying to do is, one of the problems we have with the system today is that when things get really bad, many of you who've worked in OpenStack have probably seen this, where the queue builds up, everything is getting thrashed. You put a patch up, it doesn't work. You call recheck, and everybody else is doing the same thing. So now we have a finite number of workers, and now we've exhausted our quota for resources, and everything's taking hours and hours to run, and everything's just really, really slow all of a sudden, and it's really painful for everybody. And this generally happens when we have too many bugs in the system. So we're always going to have a few latent bugs in the system. That's sort of expected, but they build up to a certain threshold before you notice them. And by that point, it's really too late. So one of the things we're trying to do is actually, we have a manual process to promote bug fixes to the top of the gate queue. So they could skip ahead. And we're actually, one of the plans, we discussed actually this mid-cycle in Germany, is to automatically be able to promote bug fixes if they have a fingerprint and elastic recheck. So this should help the process of actually getting these bugs fixed. So if everything's really, really broken one day, and we have a patch that we'll think will fix a lot of things, we could put this in and automatically promote it to the top and hopefully get things fixed quicker. Want a better job of actually presenting this data to people. There's a bit of sort of hidden knowledge in this, and you have to stare at it long enough to figure it out. You want to be able to present patterns and patterns better. So we have a failure, we have a fingerprint. We could show the trend of the fingerprint. But is this a Postgres-only failure? Is this on one provider? Is this a rack space or HP problem? There's other ways we could slice the data. We have a lot of metadata, and being able to present that metadata much easier. You could actually go to logstash.openstack.org and see that, but it's not really that easy if you don't know what you're looking for. One of the problems we have now is we could tell you this bug was seen 80 times in the past 24 hours, but that doesn't mean anything. Like that just means that's a raw number, but trying to put that in percentages, actually we haven't done that yet. So we can't say this bug has caused 10% of the failures in the past 24 hours, or even 10% of the jobs to fail. So we don't actually have any nice ways of doing things like that yet. Another thing I want to do, and we talked about this actually recently, spoke to some people about this, is packaging this up for downstream consumers. It turns out running running tons and tons of small OpenStack clouds is very similar to running one really, really big OpenStack cloud for a very, very long time. And in fact, it actually is even better than that, because by the time we ship code, we actually are shipping with known bugs. And we have a list of the known bugs in here now. And so if you're a downstream consumer of OpenStack and you want to monitor your system and debug it and things like that, make sure it's working, we would like to make Elastic Recheck work for them as well. And we can actually you could actually see when a known failure has hit you. And another thing we have a problem with is we have a huge Elasticsearch cluster. We're trying to figure out a better way to move forward. Some ideas have been floating around for a little bit. One idea is to move away, put a JSON logger in. And the problem we have now is we take all this formatted data from Python, we're putting it in random junk in the log formats. Then we're parsing it again on the Logstash. And that's a lot of extra work that doesn't need to happen. We're serializing and we're putting in a string and taking it out of a string for no reason. We probably could cut that whole step out and save a lot of work for ourselves. And so we're trying to, every so often, we'll actually see, due to some assorted problems, we'll actually see the Elasticsearch cluster get backed up and trying to figure out how to do a better job of making that not happen. I'd like to thank everybody who's contributed to Elastic Recheck. A lot of these have been people who've put fingerprints in. And if you haven't yet, it'd be great if you could go and give us a hand on this one. Another actually really big part of this is actually fixing the bugs. This is really the first step in wrangling some of the failures we have in OpenStack. The first step is knowing why it's failing. So now we actually have a pretty good insight into why it's failing. And the hard part is really fixing those failures. And so we have, I'll show you this in a second, we have a huge page of bugs that are open that are causing all kinds of pain for everybody. So thank you, and I'd like to show you one more thing. So this is not working. Let's see if this, there we go. So this is the page today. So you can see here, this is the biggest bug we have now, and I think this was caused by a patch recently proposed in Nova as a database migration. And we need to sort out the proper way to fix that, because we can't actually revert database migrations, because we have to assume somebody's been using that database migration, and we can't break the migration path. Otherwise, we could get in weird states for upgrading. We have a deadlock here in the scheduler. All kinds of crazy bugs. So here you can see this is a Nova bug in progress. This one is a CI bug. Nodes allocated node pool are very slow. I just love that title. We have all kinds of things here. You can see the new one. So this is a nice example of why this is really useful. We can actually see this bug came up on July 30th. So you can actually go through the logs in OpenStack, and we could actually look for anything that sticks out. So we found the stack trace, and you can actually go through. It took about 5 minutes to go through the OpenStack logs and see, oh, this was committed on this day in this window. It's probably the cause. We've had this grenade bug for quite a long time. We have all kinds of crazy bugs. New releases of things break things. SQL Alchemy 095 broke the world, and it apparently came back. This may be a fault, a red herring, actually. This may be a different bug that it caused the same fingerprint to trigger. This is actually one of the problems we have right now, and it's a hard one to fix, is getting really good fingerprints. The logs are really not great all the time, and we try to do our best job of finding a single line that will show a bug happen, but we can't. It doesn't always work. Sometimes multiple bugs will hit the same thing. As you can see, this list goes on and on and on. And we have bugs. This happened, one time in the past 24 hours and 10 times in 10 days. So this is a really serious bug for us. But in the grand scheme of things, it's not. Here's one. This happens very rarely, and it keeps going down the list. So we don't have just a few big bugs. We have tons and tons of small ones. or Apache failing to start happens very rarely, but it still happens. And then we have another page, which is our unclassified failure rate. And so you can see here we actually break it down. So we could look at the past 24 hours. You can see this one has a huge number of failures the past 24 hours. There's actually a patch up to fix this one, or to detect this fingerprint. And you can actually look on the right here. And you can see, if you're working on a project, you can pick your job off this list and just track it and take a look and make sure you don't have too many failures in it. We get really strange unit test failures every so often. Let's see if this will load. So no matter what the job, we're probably seeing these failures. And these are all failures in the gate queue only because we assume the check queue is full of too much dirty data, but the gate queue, we're assuming everything has had to pass several rounds of testing before it makes it in. And my connection is apparently really slow right now, so no logs for you. Any questions?